Okay, that's our today's colloquium. Thank you very much for coming to this meeting and also for joining offline. I guess I'm supposed to say something about the organization of this colloquium. So this is the weekly colloquium organized by Research Center of Quantum Physics. And this time it is also co-sponsored by the Indonesian initiative, Quantum Initiative, yes. And today's colloquium is also the first colloquium in this year, 2025, which is declared or designated as the International Year of Quantum Science and Technology. For celebrating 100 years anniversary since the invention of quantum mechanics or matter mechanics by Heisenberg. And in today's colloquium, we are very lucky and we are very honored to have Matteo as our speaker. And today he will speak on his research on quantum network, simulation of quantum network using satellites. And before that, let me briefly introduce Matteo. So, Matteo is doing a postdoc in Sorbonne University under LLB, and he obtained his PhD in Padova University and in science, technologies, and measurement for space in 2017, and afterwards he did some postdocs, including as a prestigious Marie Curie postdoc also in Sorbonne University. And right now he is a research engineer also in Sorbonne University, and he is doing research in quantum network, as I said. Matteo.
Okay, thank you everyone. I'm Matteo Schiavon, as you presented me. Thank you for the opportunity for speaking here. And in this presentation, I will speak about how we can use satellite to do quantum communication. So to start, I wanted to give a brief introduction on what is quantum communication. You know that communication means that you are transferring some information from one place to another place. And classically, the information is encoded in bits. A bit is just a two-level system, 0, 1. So, okay, so this is what you can do classically. But you know that actually nature follows quantum mechanics. So when in classical physics you have a two-level system that can be 0 and 1. In quantum mechanics, the two-level system is actually, you can have 0, you can have 1, but you can also have a superposition between 0 and 1. And so you pass from the bit, that is the classical digit, to its quantum version, that is the qubit. And what is the important characteristic of the qubit? Okay, with a qubit, normally you also encode one bit of information, but the important thing is that you can encode the bit of information to what you call complementary properties. That means that if you are encoding in one property, your bit, the other property is completely undetermined, undefined, we could say. So, for example, I put here 0 and 1. If you use 0 for bit 0 and 1 for bit 1, and then then it means that these other properties, diagonal and anti-diagonal, I could say, this is completely undetermined. But if you encode 0 with this bit, with this state and 1 with this state, these properties completely undetermined. So this is a very important thing that you use in quantum communication. Okay, then that was the theory. Then in practice, when information is carried by some physical object, and the physical object that used to carry the information is the electromagnetic field. And you know that the electromagnetic field is quantized, and the quantum of the field is a photon. So you can use a photon to encode your information. And that is what you do in discrete variables. Actually, in discrete variables, what you take one single photon, use two different modes of the single photon, and these two modes, they give you the 0 and 1, the states 0 and 1. And then you can take the superposition of the two modes to the complementary property. Like, for example, in polarization, you have a diagonal anti-diagonal polarization. So what you need for discrete variables here is discrete because you need a discrete number of modes, and you are encoding and you are exploiting the fact that this mode, you can superimpose these different modes of a single photon. And you can use different properties like the polarization, the one that I said, that you use the time beam, the different timing of the pulse, you can use the path. And all this is what you call discrete variables because you have a fixed number of modes. Actually, is a fixed dimensional system. But you can also encode information in what you call the continuous variables. What are they? Actually, as I said, the carrier is the electromagnetic field. If you take a monochromatic electromagnetic field, you can say it's a monochromatic wave. And actually, you know that a wave is described by the amplitude and the phase. And in quantum mechanics, you have the amplitude and the phase that are also complementary properties. So, roughly saying, if you are encoding information in the amplitude of your wave, the phase is completely undefined. On the other side, if you are encoding the phase of the wave, the amplitude is completely undefined.
So the amplitude is more like P and phase is Q up.
Somehow, yes. Okay. That was a very rough way to describe it. Then if you want to have the real correspondence between Q and P, you just need to pass from the polar coordinates, like the amplitude and the phase, they are polar coordinates. You go to the Cartesian coordinates, and those Cartesian coordinates, they are behaving exactly like Q and P. So this is roughly. It's just simpler to see that, but the one that you are actually using are the two coordinate Cartesian coordinates. But we can use that, and the important property is that they are also complementary, the two. So using that, you can do quantum key distribution. How can you expect this to transmit information securely? Well, what you have, you need complementary properties, and you need to choose randomly in which of the complementary properties you are encoding the information. Then, after you exchange all the information, so after all your states have passed by the channel, and you assume that the channel is controlled by your adversary, after that, you are communicating which property you used for encoding each bit, I would say, each state. And then, why this is important? Because actually, the adversary cannot exploit the information about which property you have used to interact with your state, the channel. So you have to interact not knowing which property you have used. And so this interaction is forced to introduce some errors. And in the discrete example, in the discrete variables, you see that as a bit error. It means you are sending a sequence of bits, and then the bit that you receive, they have some errors in between. In the continuous variables, you have something similar. You see actually that the two, like say, quadratures, they have some fundamental quantum noise, but if you have someone in between that is spying your communication, you see that this noise increases. So by using measured errors or the noise or the increasing noise, you can see how much information are leaking to an adversary. Yes.
Is it normally to have two complementary variables, or it can be more than?
It can be more than that. For example, in polarization, you have three mutually unbiased bases. You have a horizontal vertical, diagonal anti-diagonal, and the left and right. And in principle, you can encode the information in all the three of them. So there are, I say two because you need at least two for non-complementary properties to do QKD, but you can use more.
Depends on the schemes you are using.
Yes, and in polarization, you are actually the maximum mutually unbiased basis is 3 because it's a two-dimensional Hilbert space. But if you go on with QDs, you can have more. But it's just more tricky to do experimentally. Then.
The last point is just the trade-off between information gain and errors.
The last point actually is just a way to say that you measure the errors or the increased noise, and you know that you can know theoretically by the security proof, you can link this error or increased noise to how much information you are leaking to the adversary. So, okay, so actually you have, you know how much information, mutual information you have between Alice and Bob. You know how much information you are leaking to the adversary by measuring the error. And if the information you are leaking is lower than mutual information that you are exchanging, you have some classical procedure, some privacy simplification procedure that allow you to be sure that the shorter key that is given by the difference of the information is information theoretically secure. That is the idea behind it. Okay. So yes.
To ask questions.
Yes. Okay. So that was the first application of quantum. I would say of quantum information, of quantum communication. It was quantum key distribution, but you can do much more. Actually, the much more is what you normally call quantum networks. And quantum networks, they're based on the distribution of entanglement. Entanglement, okay, entanglement is just to say, we saw that for a single system you can have like complementary properties, but that you can also have in multiple system, in compound systems. And in particular, you can have a compound system that are correlated in complementary properties. And when you have a compound system that are correlated in complementary properties, you call that entanglement, actually. And if you are distributing entangled states, you can build much more complex protocol with respect to just quantum distribution. And okay. But the problem is that distributed entanglement is trickier than just distributing quantum states. Why is it trickier? Okay, because okay, you know you have losses. We'll speak about that a little bit later. And also, for building up huge quantum networks, you need to have some other building blocks that are very difficult to build, actually to produce, that are quantum memory and quantum repeaters. Quantum memory is a place where you store your quantum information. And the quantum repeater is just a system that if you produce an entanglement pair here and an entanglement pair here, you make a measurement here so that these two nodes, their entanglement one with the other. And that is a quite challenging part that I will not speak of directly in this presentation. But it is what you need for producing a quantum network.
It's trusted. Okay,
trusted node means that is a node that, okay, for example, in quantum key distribution, you would say you can exchange, let's say that you want to exchange a key between this node and this node, but you are too far for having a direct connection. So you can exchange a key between this node and this node, and between this node and this node, and then make the XOR of the two keys so that you have a key from this node and this node. The key is secret, but this node knows it. In that sense, the security is based on the fact that you trust this node in between. So trusted node is a way to say is how you build actually qubit networks nowadays. You have some nodes in between that you know that they know the key that you are exchanging, but you are trusting that they're not using, that they're just discarding them one, and that you are not giving them to the adversary. That is the sense of trusted nodes. And I think you can have something similar for the network, that just I don't know exactly how it works for a network, the trust or not trust. But for QKD is not a way that you can go very distant. The only way, well, actually you have another way, that is why people are interested in satellites. Because, okay, here I think this graph is quite evident to say how the losses they scale with distance. This is the losses in decibel. So this is algorithmic scale. And for the fiber, they are exponential, the losses. While if you go on free space or on satellite, they are not exponential, but they are quadratical. And why? Actually, the fact is that, okay, optical fiber, they are very good. They guide your light between even the band, but you set the light on one part and you receive it on the other part. But they have an absorption all around the fiber. So this is the formula for the absorption, and this is exponential. This is what gives this exponential behavior of the losses. In free space, you have something similar. In free space, I call it, you have one telescope here and another telescope here, and they are going through the atmosphere. The atmosphere has some losses also, some losses that are exponential. Normally, at least for some, there are some wavelengths for which these losses they are lower, at least in clear sky. And then you have another term that is given by the diffraction, because in free space, your optical beam it just diffracts. It just is enlarged. So if you have a fixed aperture telescope, it means that it's going bigger, and so you collect less light of what you're seeing. That is for the ground-to-ground, but if you're going to satellite, this is even better, because of the satellite, most of the propagation is in vacuum. And in vacuum, you don't have any absorption. And you have only the last 10 kilometers, let's say, where you have absorption. And that is the same if the satellite is 500 kilometers, 1,000 or more, because the atmospheric part is always like 10 kilometers. And so this is why the losses scale only as L-2. It's only the diffraction term, and not the absorption is like fixed.
Somewhat counterintuitive that in space you have less loss. Loss here means the number of photons that does not.
Yes. Yes. Actually, okay, actually I put the free space here, but the main that you can compare there are two. They are the fiber and the satellite. And the satellite you are gaining, because actually the atmospheric part is limited. That is a little bit what gives you the advantage with respect to the optical fiber.
So for very long distance, satellites and free space is better than.
Yes, I would say satellite, because free space, you have like the curvature of the Earth. Free space, ground to ground, you can have 150 kilometers, I will show later, but more is challenging. It's satellite that is the most, would say, promising way to have a long distance.
For short distance, optical fiber is better.
For short distance, optical fiber work very well. Also, the losses are less, and also, I mean, if you go also here or here, I mean, it doesn't make sense to have a satellite for 100 kilometers.
What about the transmission speed?
The transmission speed, okay. If you say the key rate, it means how many bits you are producing. That depends a lot on the losses, because it means that okay, when you are sending, the speed depends how much of what you send you are receiving. So the higher the losses, the less bits you are receiving, and so it means that the key rate is lower. In that sense, the speed somehow depends on the losses. For concerning like what in internet, normal internet, you say the jitter, normally is not a figure of merit that you are considering in QKD. Like it's not called the jitter, it's like the ping. You don't consider it normally for QPD. Okay, so just to say that my presentation is like, okay, that was just the introduction. Now I will like speak a little bit of the story that led to satellite quantum communication. Then I will speak about how you can model the quantum channel. That is like probably the big part of the presentation. Then I will speak a little bit about other satellite projects that we have in our group in Paris and some future perspective. Okay, how to model the quantum channel. This part is like a combination of part of work done in other research group and work done in our research group. So, okay, so start how people arrive to satellite quantum communication. Well, actually, people started thinking about doing satellite quantum communication quite early, let's say. These, I just saw some quite early experiment. I think this is like probably the first experiment that I saw about doing some something that would lead to satellite quantum communication. And of course, people that were doing in ground-to-ground channel, because they say ground-to-ground channel, you have the atmosphere, and the strength of the atmosphere somehow, if you go quite far, it can be comparable to the atmosphere that you have in the satellite channel. So people said, okay, let's put two telescopes some kilometers apart, and then we have some benchmark for satellite quantum communication use. And quantum key distribution is the first protocol that is always tested when you do quantum. So 98, the first one, then they went like between mountains. This is in the Swiss Alps. Then this is another experiment from the sailing group in Wien, from the two sides of the Danube river. And then here, actually, this is like I would say, the most advanced free space ground-to-ground experiment that they did in the Canary Island, where they have, I think, the longest ground-to-ground channel that you can have on the ground that you can exploit. It's 144 kilometers. And they did some, in this case, is a normal QPD experiment using an entangled source. So this is how it started for doing ground-to-ground experiment. But then, okay, you're saying, for example, in this case, you have quite strong turbulence, much stronger than what you expect for a satellite, but still you're quite far from from building actually the actual satellite for quantum.
All this you're saying discrete variables?
Yes, yes, they are all these experiments, they are discrete variables. Continuous variables on free space, there are very few experiments for what I know. There are discrete variables. Then, okay, then the group where I did my PhD, actually they said, okay, why cannot we do some simulation of some feasibility study using satellites? And they were, this is much before I arrived there. They said, okay, you have some satellites that are built for geodesy that have like corner cube reflector on them, because there are some quite big network of satellites that are there for studying like just the orbit of the satellite. They put satellites, they do a very precise orbit determination by measuring the distance of the satellite, and with that they can do geodesy studies of the Earth gravity, let's say. So how can they do that? Actually, they are measuring the distance between the satellite and the ground station using a laser ranging. They shoot a quite strong laser towards the satellite, and they measure the time of flight between when they send and when they receive. And with that, they can measure the distance of the satellite with like they arrive to centimeter or even less, or even better precision for the distance. So people in Padova said, okay, for doing laser ranging, you need quite strong laser. What if we attenuate the laser that you are sending so that what is reflected by the satellite is roughly single photon? And with this idea, they actually were able to construct a simulated single photon source from satellite. Okay, let's say attenuated laser source, not the really single photon source. But this is actually what you need for QKD. And so using these emulated source, they were testing like some encodings. They tested the polarization, they tested time being encodings, and they demonstrated that they were feasible to do QKD on them. And that was a strategy that was also employed in parallel by a Chinese group, by the Januari group. But let's say this leads us directly to the next step. Because actually the Chinese group, they did something more. They built the satellite. And they sent the satellite to orbit, and they did all the stuff that was done with the emulated source with a real quantum source. The satellite is Michus. Actually, they used it to do quantum distribution, prepare a measurement. It means you have the source on the satellite and the detectors on the ground station. You just do QKD. I think, no, I didn't put an image of the satellite. But then they also put an entangled source on the satellite, and they were doing entanglement-based QKD. Means you have the satellite, you have two entangled photos, you send one photo to one ground station, the other photo to the other ground station, and you can exchange a secret key between the two ground stations. Then they were also doing some more complex protocol. They did like ground space teleportation. Is actually quantum teleportation is a protocol that allows you to teleport a quantum system from one place to the other one. And what they did, they exchanged an entangled pair between the ground and the satellite, and then they did the teleportation of the photon from the ground to the satellite of the quantum state. That was what was done with this satellite. And then now is more or less is a recent slide that I prepared to show a little bit how is the international background, the international situation for satellite quantum communication. There are some satellites that have already been sent: the Singapore satellite, the Michus satellite, the Japanese Socrates satellite. This is a source, just a source of polarization photon, and prepare a measurement with just two non-orthogonal states. This is an entangled source, but the first satellite from Singapore, they didn't have the telescope. They just had the source, they were testing the source inside the satellite. And then Michus is the satellite I already spoke about. And then the Chinese, they just sent another satellite. They just put out the first results, but I don't know yet. I didn't read the article yet, but they're doing that with the micro satellites. And then you have plenty of other projects. Now, many people, they're going towards the CubeSats because they are simpler to build. They are more, they are cheaper also. So you have some projects, the UK from the ESA, European Space Agency. You have some project in Germany. You have in Singapore, they are going on with the CubeSat development. And then you have some other like bigger project. For example, in Canada, they are doing research on a microsatellite. It's quite long. It's like since more than 10 years ago that they are developing it. Then in Europe, you have Eagle One, that is a QKD satellite that probably I think will be sent like next year or this year or next year. And then you have like two. Actually, you have in the United States, apparently Boeing is building a satellite for with an entangled source in it. And there is some preliminary study in France for building a satellite with also an entangled source in it, but we are speaking like maybe 2030. So it's like it's on the quite long range. Boeing, I think I heard 2026. They were saying about launching, but I mean, I didn't have more updated information. But so what can you do before you have the satellite? You can, okay, in order to know how to build a satellite, you can model the quantum channel. And how can you model a quantum channel? Now, okay, what you can do, you can decide which is the main characteristic you want to consider in the channel, and you build a model from it. And I will show that you can build model going from simplest one to much more complex one. Actually, the simplest one is the one that says I just consider the diffraction. So the only effect that I have is that I have a telescope here, a finite aperture of the telescope, and the diffraction, I have my beam that is enlarged. So this is a very simple analytical model, the diffraction. And here, if you see, this is just using Gaussian beam propagation. And you see from the transmittance, calculated transmittance, you found out the 1/L square law that tells you how much the transmittance is for the satellite channel. So with that very simple and basic model, you can already see what is kind of one of the big takeout from satellite quantum communication, that the bigger the telescope, the better.
So W is the width.
W is actually the size of the beam at the transmitter.
Is the distance.
Okay. This is the beam waist at the transmitter. So, okay, you have the transmitter there. Okay, we are doing the assumption, a very rough assumption, that we have a Gaussian beam at the transmitter. And the Gaussian beam is characterized by the beam waist, that is the radius of the beam. And this is the radius of the beam at the transmitter. So, of course, if you see the bigger the radius of the beam transmitters, the bigger the transmittance also. Because the smaller beam, they diverge more. Bigger beam, they diverge less, and so you can collect more of the power for larger beams. But normally when you do satellite to ground, you consider that the size of your beam at the satellite is limited because you cannot fit a too big telescope on the satellite, while on the ground you can get bigger. So this is why you say larger telescopes are better, because you are considered a telescope on the ground. And actually, here I showed just some very simple simulation on how the losses they go with respect to the telescope diameter for different satellite distances. And you see that 1.5 telescope, they go down quite fast, the losses, if you get bigger telescopes. This is the telescope they have in Matteo, where the Paolo Violesi group was doing the experiment. And that one, I think it was, there are other projects with other possible telescopes that they want to build. So that was another reference they put there. But that was the first. Then you don't have only the diffraction, you have also other effects. And this is another quite simple model where you can see a little better what happens. This is called the absorption diffraction intrinsic loss, where you have your losses, you have the diffraction where you were saying before, and you have the absorption of the atmosphere, and some other losses that are given by, for example, your optical setup on the ground station. This model is also quite simple. Okay, this is a sum because I'm doing the losses in decibel, so it's logarithmic, so you're summing the different parts. And this model is quite good also for starting points to have an idea how you can optimize your satellite orbit, because it's very simple, it's analytical, so you can do a lot of optimization on it. It doesn't take into account all the effects of the turbulence, the atmospheric turbulence, and the effect of the pointing error. It means that the satellite is not pointing towards the ground station, but is pointing a little out from the ground station. But since it's computationally efficient, it's still quite useful. And it has been published quite recently, and it's also open source. This model is from the Strathclyde University. And so this is the first thing that you can do, that you can start being a little more realistic. Then you can add more effects. And the more effects that you can add, I was saying before, you didn't take into account the effect of the atmosphere and of the pointing error. and you can add them, then in an average way. What does it mean? Okay, because actually the atmospheric and the pointing, they're actually statistical phenomena. So that means that actually they change with time. They're random phenomena with some probability distribution. In this way, with this model, it's also quite simple. You are just taking the average of this phenomenon. So, for example, when you're doing discrete variable, this is good because actually you want to have the average of how much photons you are receiving. So this is also quite a simple model that you can use for doing other testing about products. And actually, this very simple model is used quite recently by a work that I will show a little bit later on entanglement distribution from satellite. And this is another work from other theory people in our group that were studying more the effects of routing entanglement between satellite and ground stations. Actually, they were studying the protocol for routing the entanglement between different ground stations using a satellite in between. So, and that was done with this average model. So with that, you can already do quite interesting works on satellite quantum networks.
How should we understand the graph?
The equation? Oh, the graph. Okay, sorry. This is okay. The graph. Okay, this is just the orbit of the satellite. You have a satellite. Okay, you have like we consider two ground stations, Paris and Nice. Paris and Nice is the south of France. And you consider a satellite that goes in a polar orbit. So it's like this is the Meteus satellite. So it goes around the pole and then it goes like that. The Earth rotates like that. The satellite is doing like that. So what we see here is that okay, it's doing mostly like that. Okay. What you see here is that the satellite passes on top of Nice before passing off top of Paris. So here you see that the distance from satellite to Nice is lower here, and then so it passes by on top of Nice, and then it passes on top of Paris. And this is the elevation. So this is the angle, is actually the angle from the horizon that you see, for which you see the satellite from Paris and from Nice. And actually you see here that you have some points where the satellite is quite high for both ground stations. So you can actually do entanglement distribution between the two. You just point one telescope to Paris, one telescope to Nice, and you send the photon to the two, and you can receive it from in both. Here we did the simulation of the atmospheric transmission between the two, because the transmission depends on the altitude, because the lower the satellite, the more quantity of atmosphere it crosses, and so the higher the losses because of the atmosphere. And then is the total downlink attenuation that we simulated. And that you see also that you have this, it reflects quite well the orbit here. And you have like some part here, I would say some region here where the losses are fairly acceptable for both ground stations. And so you can do entanglement distribution. Okay, then you can go a little step further. Because I was saying the model that I was showing you before, you just calculate the average. It means that in a single point, you have that your channel changes, but you're saying, okay, the average transmission for this point is this, for this point is this. But then if you watch, actually, the total probability distribution, that is not the average, is I could say, since it's a random event, the transmittance is drawn from a probability distribution. Why? Well, you can just imagine this is the most simple case. You just imagine you have your satellite and your ground station here. Since your satellite is not pointing well at the ground station, the beam is like entering and exiting your telescope. And so the transmittance is like going high and low randomly, I would say. And this is, for example, for a single point, I would say, you end up having a probability distribution that has this form. this is here is when the beam is exactly pointing the satellite, and here is when the satellite is not pointing toward the center of the ground station, but is going out in one direction with respect to the ground station. So for each point of the orbit of the satellite, you have a probability distribution that has this form. But then, as you saw in the last slide, the satellite is like rising and going down. So the distance is changing. And you can also see that how much your pointing error is the effect of your pointing error depends on the distance, because the pointing error is like an angular error, and what you have on the receiving plane depends on the distance, because just the angle times the distance, it gives you the spatial movement of your beam with respect to the ground station. So you have different probability distribution of transmittance for each point of the orbit. If you integrate them together, you have something that has this form, where this is when the satellite is on top, and then all this tail is when the satellite is going down, on one sense and on the other sense. And then, okay, these are thing is that because actually you start tracking the satellite at a certain altitude. So let's say 20 degrees, from minus 20 degrees to plus 20 degrees. This is when you are tracking your satellite, and so you end up with a probability distribution that's this form. And then you see that the probability distribution depends on the satellite height. Of course, the larger the satellite, the bigger is the maximum transmittance, because you have less diffraction losses when the satellite is on top, let's say. And the probability distribution, okay, so you can build the probability distribution at efficiency, and if you just consider this effect, you have that this is a viable distribution. So this is why it's a log negative viable probability distribution. Okay, but then in that sense, we are only considering the fact that you are pointing in and out from the ground station. But then you have that the atmosphere, you have other effects that you have to consider, because you have your wave that is propagating towards a medium that is like randomly changing. And what makes you is that if you have like, assume that you have a planar wavefront that is going from your satellite to ground station. Each small portion of the wavefront, they see a different refractive index. So when you arrive towards the ground station, the phase, instead of being like a plane wave, is like the phase profile is very, very perturbed, I would say. And then if you want to couple into single mode fiber, you have that this very perturbed phase profile is not well coupled into the fiber, because the fiber couples well I would say it's like doing a spatial filter, a very strong spatial filter. If your wave is like making, I would say, the projection of your wave profile with the single mode fiber profile. So if you want to couple it, if you just take the signal from the satellite, the coupling is very, very bad. So you are having a lot of losses just because your beam that is entering the telescope, it just doesn't match what is actually going to the fiber. But this is something that you didn't see in the model before, and so you have to do something more to take it into account. And this is what we did in collaboration with an adaptive optics with some atmospheric institute in Paris. And actually, we evaluated how much you can how strong is this effect and how much you can correct this effect by using adaptive optics. Okay, I didn't prepare a slide on introduction of adaptive optics. Actually, the idea is that, as I said, your wavefront is very perturbed when it arrives in front of your receiving telescope. But then, what can you do if you want to improve it? You can actually put your wavefront, you can make it reflect by a deformable mirror, and you can like adjust the mirror, I would say, so that you are doing inverse transformation of your wavefront. So you start with a plain wavefront, then it's you have a perturbed wavefront, then you use the mirror so that you end up with another plain wavefront again. Wait, let me check if I don't think I put is what here I was putting just adaptive optic correction. It was this, but I didn't put the image. I'm sorry. And so with adaptive optics, you can actually undo the effect of atmospheric turbulence and maximize the coupling into the single mode fiber. Okay, so then you can have different strength of adaptive optics. It depends on because as I said, can I use the blackboard?
Yes, please.
Okay.
How much you can improve this inductive?
Huh?
How much you can improve?
You can improve quite a lot.
Okay.
Okay, thanks. Thank you. Okay. This?
Yes.
Okay. Let's assume here I have my wavefront arrive straight in front of at the entrance of the atmosphere. Then here you have the atmosphere, and so my wavefront is takes this form. Then here I have my receiving telescope. And then, okay, I'm producing my wavefront. The telescope is just taking the pupil and reducing the size. My pupils, I have my, here I would say I have my very bad wavefront. Here I put a mirror that is deformed. It means that you can change the size of the mirror. You can change the optical path of your mirror for the different part of your wavefront. Then, okay, then here I put, okay, put a split, and here I put what you call a wavefront sensor. So you are measuring actually your wavefront, and you can do a feedback loop so that your wavefront here is plain again. Of course, and then so when it's plain, then you put the lenses here and you couple it to single mode fiber. That is how it works. This is the principle of adaptive optics. And actually, here, how good you can do that depends on how dense are these actuators on your mirror. Of course, if you have just, assuming if you have just one actuator, you can just do TT, so you can correct very little. If you have an infinite amount of actuator, you can correct, yes, all the wavefront, and you can couple perfectly. But in reality, you need to have a drawback between how many actuators you have and the cost of your system, because the more actuator, the more complex your system. And here you see actually from going to allow number of actuators to a higher number of actuators, then the coupling efficiency is actually quite strongly influenced. Here, for example, when the satellite is on top, with these adaptive optics, you have 30% coupling efficiency, but with these adaptive optics, you have almost 65%. And this improvement is also for the lower elevations. And for 20-degree elevation, you see that the improvement is even more drastic. So actually, this is important if you want to do QKD, because actually you cannot just ignore this effect. It's quite strong. And if you saw you saw here this probability distribution here, it is quite smooth, I would say. Just imagine you take one of these curves, and then you see here what changes if you are changing the adaptive optics that you are using. And you see that, think one of the curves of those plots there, it can change. You have these 4 plots that where the difference is only how many actuators I put in my receiving mirror. So how strong is my adaptive optics there? So this is an effect that cannot be neglected if you wanted to do a reliable quantum key distribution, a reliable satellite simulation of the quantum channel. So, okay, so finally the transmittance of your channel is the transmittance of the atmosphere, the beam wandering effect, and the single mode fiber coupling. And then using that, you can build the probability distribution of transmission efficiency for the whole passage of the satellite. And we did that. We studied that for like 1.5 meter telescope. We studied that for a quite good active optics. And for a different height of the satellite orbit. And we studied that for daytime and nighttime operation, and for discrete variable and continuous variable quantum distribution. We performed the simulation, and actually we showed that you can perform a quantum distribution, but with discrete variable and continuous variable, but in daylight and in nighttime operation. And then we studied that both in the asymptotic limit and with the finite key. Finite key means that you are taking into account that the transmission time is limited, so you can exchange a limited number of pulses. And so you have less statistic to calculate the parameters of the channel. So you will have a statistical error that is higher. And so we get a worse estimation of the channel parameter, and so you get a lower key rate. We have to assume that the PIVA is much more powerful than she is actually, because we have not enough statistic to know how much information she gets. But actually, we showed that it's possible, in principle, to have a quantum distribution, but with in nighttime and in daylight for both discrete variable and continuous variable. Of course, discrete variables, it works way better than the continuous variables because they are more resistant to losses than continuous variable. But in principle, you can also do quantum distribution using continuous variables from satellite, using a realistic channel model. And okay, something that I didn't tell, why did you need this complex model? Cannot you just use the average model that I described earlier? Well, for discrete variables, actually the results that you get here, they are the same that you get using the average model, or comparable, I would say. The problem is that for continuous variable, you cannot do just the average. Because in continuous variable, as I said, you estimate the information that you're leaking by looking at the noise on top of the fundamental quantum noise. And you have that if the channel transmittance is varying, I would say, there is an added noise that is proportional to the variance of the transmittance due to the channel. So if the channel has a big variance, if the transmittance of the channel has a big variance, it translates in a bigger excess noise on top of the quantum noise, and that translates to a worse key rate. So this is quite important for continuous variable to take the whole probability distribution. And this is why we developed this whole probability distribution model for studying CVD.
This gives you some sort of theoretical limit, right? Where how much you can actually spend.
Okay. There are some works about theoretical limits. We didn't put it in this paper. It's more. I think they are above these limits. It's
More like simulation.
This is simulation, yes, but there have been some works on by Stefano Pirandola on some theoretical limits for free space and satellite quantum distribution. They are quite tricky. They're based on some. Still, you have some assumption of the channel for doing that. The channel model. The channel model is not probably the best, the most complete one, but still you can have some fundamental limits for free space and satellite quantum distribution.
We are talking about this paper written by 4 guys.
Yes, the plot PLOB. PLOB is for a fiber. Then Pirandola did something similar for the free space and satellite channel. I'm not speaking about that because it's, I mean, it's quite a long paper. It takes quite long to. I read it, I think, once only, and I didn't digest it very well. But it's also based on some assumption of the channel. He's doing some channel model that is quite similar to what you see here. So this is somehow parallel research. He is more interested on the theoretical part. Here is more focused on the application part. So here we are considering a more realistic way to model the channel. I would say this is the main difference. This is more towards how you can do on the experimentally.
Which one is more robust in terms of data?
The discrete variables is more robust in terms of losses, but that is something that is quite well known. What was shown here is that theoretically you can do continuous variable from low Earth orbit satellites, like until 600, 700. Then also these results are based on some assumption that you have on like the phase recuperation, for example, on the excess noise that you have produced by your source. So also here you have some assumption. Here just a first word that says in principle it's possible. It was the starting point for our successive research, but it's not like, I would say, that just tells you, okay, you can do research on that. It's not, it's completely impossible.
People seems to drop abruptly after some distance.
Yes.
Why is that?
Okay, for discrete variables, the abrupt drop is when the quantity of photons that you receive is the same level of your dark counts, because your detector has some dark counts, some counts where you don't have any photons. You just have some random photon that it's random click in the detectors due to some experimental property. I would say you have your detector, you have a completely blind case, but sometimes, for example, thermal effects, you have an electron that is produced and that produces the avalanche, so you have a click without any photon getting there. When you're, of course, these random kicks, they have a 50% couvert because they can be on both 0 and 1 detector with the same probability. And when your quantum signal that is arriving is lower than your dark count, you have that the error is mostly the error of the dark count, so it's 50%. So you can no longer have a secret key. This is the approved case here. The approved case here mostly is because actually here you are considering that your reconciliation is not perfect. So you are losing some mutual information between X and Bob. And this is the case when actually the information that you're assuming that is leaked is more than what you can recover of mutual information between X and Bob. So a certain moment when like the mutual information between the two is lower than what you have to assume that your adversary has. So this is the effect of this approved. But you also see this is a asymptotic case. You also see that this approved rule is also in the asymptotic case. Here, you should have also here somewhere. It's just we stayed until 2,000 kilometers. So you still don't see these two cases, but you start seeing here.
By bits per cyber, you mean the number of bits that can be extracted?
No, this is okay. This is number of bits, and this is the symbol. It means one pulse. So you have some pulses with some coordinate state. For each pulse, you can extract those secret bits. So it means this means that they extract one secret bit every 1,000 pulses that I'm sending. Okay. Okay. So we
Questions?
okay. So we went a little further. We used that model also for studying the distribution of entangled photons. And that is also a first benchmark towards quantum networks. And actually, the first thing that you do, you just see how much secret K you can have by using entanglement between one satellite and 2 ground station. And we did something similar using Paris and Nice. It's something similar to what you saw earlier. And but in this case, we also consider the effects of adaptive optics and seeing how much you have to push adaptive optics between the two ground stations in order to have a secret key. And that we also saw that you need to have some adaptive optics in order to have a secret key, because if you just, for example, in this case, you just correct the tip tint of the whole wavefront, and if you only correct the tip tint, you just receive almost nothing. You need to correct somehow some more complex atmospheric effects in order to exchange entangled photon between the satellite and the two ground station, Paris and Nice, this case. This is, we did, you see, this is the secret key rate between Paris and Nice, and you see that you need, this is until a certain effect of adaptive optics, you don't have anything, and then when you start increasing the complexity of adaptive optics, you start having some secret key. That is, and this is the first, they are important because you know a little bit how much you have to push your adaptive optics system in order to be able to do something. So it gives you a little dimension of your ground station. This is the main important thing.
Can you explain the second part?
This one? Okay, this is the quantum bit error rate that you have between Paris and Nice. And here you have almost 50% because you receive nothing. Here is the coincidence rate, means how many bits you receive on both. I'm sending one pair and I receive one bit here and one photon here and one photon here. Here I receive almost nothing. So that means that all what I receive is mostly dark counts. And so dark counts, the error level is 50%. Here, for example, this plot, I'm starting receiving something. And when I receive, for example, here, when I receive the most, let's say, here is 100 pairs per second. So here is 10, 20, here I receive, I say, 30 pairs per second entangled photons. And so it means of those 30, they are a little higher than the dark counts. So I start seeing the Q-bar that is going towards 0. But here, for example, I receive like 5 clicks per second, and it's way less than dark counts. So here the loss, they are mostly coincidence. They are mostly like one real photon and one dark count. And so this is not, they are not correlated at all. But you see, if I start receiving more real photons, here the losses, they start going down because I'm receiving more correlated photons. They are no longer like dark counts or background photons, they are real pairs, entangled pairs that are being received by the two telescopes. So this is why here the Q-bar goes down as the number of received, the coincidence goes up. Okay, then we also did parallel work. We also put our simulation that was orbit based. So you take the whole orbit of a satellite and you see what happens on the whole orbit. That is useful if you want to do quantum distribution, entanglement distribution, but if you want to study the effects on some other protocols, it might be not enough to do what happens, to see what happens on the orbit. Maybe he wants to see what happens for the single for the photon themselves. So we did something similar in parallel, but using a network simulator that is called the NetSquid, that is developed by TU Delft in the Netherlands. And is a software that is mostly built to test quantum protocols. And we were implementing the free space channel on this simulator, and we were using it to see what you can see with them actually. So as I said, the first model that you can make is the Weibull model, and so we're implementing the Weibull model that considers only the losses due to the fact that your satellite doesn't bound point good to the ground station, and we implemented it on this network simulator. And we saw actually the same that you are seeing in the last slide, like how many entangled pair you can send between a satellite and the ground station. Okay, this simulation, one thing that you have to take into account is that we are considering each qubit separately, so we are not taking into account the dynamics of the channel. So let's say you have a probability distribution or a transmission efficiency, and each qubit has a different sampling of that probability distribution. That is completely unrealistic, let's say, because if you send like very fast the qubits, let's say the channel doesn't change so fast between one qubit to the other one. So this model is actually giving you somehow also an average. But you can do this average by integrating it in more complex quantum problems. This is why we chose to use this software. And so we are doing almost the same, seeing how many entangled photons you receive, giving it to ground station. Here is Paris and Delft, and a satellite passes between them. And we did it, okay, we did it just for this, seeing how many pairs we were receiving, but also we tried to see something more like, we tried to see if we have Paris and Delft as trusted nodes, how many key, I would say, what is the key rate that we can produce in a quantum network of this form, like using 2 trusted nodes and some other nodes that connects to the trusted nodes and a satellite in between. And then we also wanted to see how if you can use like a satellite to distribute entangled pairs and then couple it to the telescope in Paris and Delft and send through a single mode fiber to 2 clients that are connected in fiber with our ground station. And actually, okay, we have that the amount of entanglement we can transfer is very low, like it's like 0.01 or even less bit for each channel use. So it's very low because actually you're considering here that you have the losses of the channel, the losses of coupling, and that in this simple model we consider fixed, the losses of coupling, and then the losses of the fiber here. Then this is quite recent work. We tried to improve this model and to add also the effects of adaptive optics also in this model, quantum network model, event-based quantum network model. So we used a model of adaptive optics, a semi-analytical model of adaptive optics, and we studied it, in this case not for a satellite, but for a high altitude balloon. So we studied how much the mean channel efficiency between the balloon and the ground station is according to the height of the balloon. Here, the height is like from 17 to 35 kilometers. So it's a different order of magnitude, but still you can do something with that. And actually, what we see is that in this case, we were seeing that actually it is not always true that the bigger the telescope, the better. Because, of course, the bigger the telescope, it means that I'm taking a bigger portion of the wavefront. So if I want to correct the wavefront, I need to have a higher number of actuators in my deformable mirror. It's because here, you can consider here, I'm taking some perturbation. If I have a bigger telescope and take a way bigger amount of perturbation. So given a fixed number of actuators, sometimes a bigger telescope you do worse because you are losing coupling efficiency. And this is what we were trying to see here. And we were trying to see using a high altitude balloons because it was something that was not considered earlier. And this is quite a recent work, so we tested in the archive like last month. So we built the model. Yes. Okay, I'm trying to get faster. Okay, so we did that, and we tried to see some I would say some schema similar to the one that we were seeing before. Like this is also quantum distribution as a first benchmark, and then we tried to see how much entanglement pairs you can distribute using like one balloon in the middle between two cities, or one balloon, two balloons, like one that creates the pairs and another one that just did a relay, and how many pairs you can transfer per second between the two. Okay, that goes to the other part. That was the main part of my presentation. Now I will do a little more how is the research now we are doing at Sorbonne University. As I said before, we proved that, okay, we showed that it's possible to have a quantum distribution with continuous variable on a satellite. And then now we are working on a European project for actually implementing it. This is a civic equity source, and we are working on putting it on a satellite, on a payload for satellite. This project is already ongoing. Now we just bought the components, and we have to test them and see that they are working together. Mostly is where we are now. And this is one first project that you have ongoing. Then, as I said, we showed that you can do civic equity on satellites on a channel that is fluctuating. But that has not been actually proved experimentally. So we were working on trying to prove it experimentally by using an emulated atmospheric channel built by using a variable optical attenuator. So actually to emulate the transmittance of the channel by changing electronically the value of the attenuator and seeing if we can still have a quantum distribution using that. That project started like some time ago. Now we are a little blocked because we need to improve our CVQD system for working for high attenuation, because we were a little blocked on the maximum attenuation that our CVQD system was working. So it's still ongoing. Then another project we have, this is more a national project that we have with the French Space Agency, and it's a project in the more industrial projects aimed to see a quantum network architecture. And this is actually studying, okay, from a more industrial point of view, how you can build a quantum network and what you can do with that quantum network. Same use case, but it's more from an industrial point of view. And we did this work, and it has been published last year, 2 years ago. And now this is going on with another project to see, like, to study the possible ground station and some. And then we are planning some proof of principle experiments for seeing some properties of the ground station that we need to have for building a quantum network. Then we have another work that probably don't have the time to explain in depth because time is getting short, and is like studying what is called twin field protocols. Okay, that would require a little of time to explain. Actually, okay, when you have an entanglement-based protocol, the problem is that you need the two photons to be received. You have the satellite, you distribute one photon, the other one, and you need both to pass. You can, people have devised other protocols that are the reverse of that, where you send one photon and you make the measure in between, and that is, and the measure actually is a correlation measurement between the state produced here and the state produced here.
So initially the photon.
No, you have uncorrelated photon, you make a Bell state measurement, so an entanglement measurement, and you actually measure the correlation between the two. And with that, you can build what is called a measurement device independent protocol. Because actually the measurement station doesn't know the photon they're sending, just knows measure the correlation. And by sending the result of the correlation measurement to the two, they can extract the secret key. Normally, you need to have, for the first protocols that were proposed, you need to have both photons to be transmitted, But then they proposed this kind of twin field protocol where you just need one of the two photons to be arriving to the ground station. It's actually is somehow built on a first order interference between the two beams that arrive from the two ground stations. And in that case, you can get better with respect to the distance. Because if you need just one photon to arrive, in this case, just with t and not with t squared, if it is a transmittance of one of the two channels. And so this, since we have the atmospheric model, we tried to see with the atmospheric model, if you can have two ground stations for twin field and a satellite on geostationary orbits. And actually, we showed that we can have secret key between the two ground stations using the satellite in geostationary orbit as a relay, I would say, as a in-between measurement station. That if you are interested, you can ask about during the thing, and then just five ahead on future perspectives. Okay, we have, as I said, we have a collaboration with the French Aerospace Agency, and they are expert in adaptive optics, and so we are studying, like, as I said, the continuous variable quantum distribution with the multi-channel. This work on twin field QKD, and also we are planning to do also experimentally and to test it experimentally. We have a PhD thesis ongoing on the subject now. Then other possible work, I had read recently this work by Stefano Pirandola, is one of the authors, for a satellite-based entanglement distribution and quantum teleportation with continuous variables. And it was interesting, but I was curious to see if it is possible to reproduce the results using a more complete model of the atmosphere, because the model of the atmosphere it was a little simplified. So and the results were already delivered. So it would be interesting to know if you use a more complex model, you still have enough continuous variable entanglement for doing something interesting afterwards. That was, but that I couldn't say it hasn't started this project because I mean it's not lack of manpower. Then there are some other French projects in France. They are now building a telescope, a 2.5 telescope, general telescope, and they are is 2.5 meters, is quite big. It's low adaptive optics, and they are open to collaboration with the institution. Okay, it's French. This is more for a French collaboration, but apart for a small part of this, the time they want to dedicate to quantum distribution, quantum protocols. So that is one possible for the research direction. And then this is this mission by the English satellite, and there is a project by ESA where they are sending is actually a satellite laboratory, I would say. So it's a reconfigurable satellite with a QKD source at 785 nanometer and a classical communication channel, bidirectional, and they are open to experiments that you can do with them. So there could be, if you want to test protocols on a satellite, as soon as they are compliant with what they have on the satellite, you can do it. For example, for classical communication, it might be interesting, but also if you want to do some particular quantum encoding, it might be possible to test it. And then, okay, finally, other possible interesting aspect is like frequency transfer to GEO. The frequency transfer are the actual technologies for techniques for transferring very precise frequency reference between two distant parts. And what we are seeing in the twin field, you need like to have this very precise frequency transfer to adjust geostationary satellite. And we saw recently, quite recently, a paper, it's like some years ago, a paper that from the Chinese group that was doing an emulation of this frequency transfer towards geostationary satellite. And I think it was interesting to see how you can do that. And it's another possible research field that could be implemented. But still, there are ideas. I didn't even have the time to read this article. So there are still possible research ideas, and that was little bit.
Thank you, Matteo, for very interesting presentations. We still have 10 minutes for questions. I expect some questions from the experiments.
There's actually one question from Zoom meeting.
Okay.
The question is, during the entangled pair purification, do you need to perform state tomography to certify its entanglement, or do you use a device-independent approach?
We don't use a device-independent approach. I mean, for at least for the protocols that quantum distribution protocol that normally people are studying, they're mostly the entanglement-based version of the BB84. So you just, instead of preparing like the horizontal diagonal, horizontal vertical diagonal anti-diagonal, you prepare the entanglement pair, and then you measure in horizontal vertical diagonal anti-diagonal on the two sides. And when the measurement basis they match, actually you have the key. When they don't match, you discard the bit. That is a little bit. Probably you can also on a device independent. It's okay. You cannot get fully device independent. Even if you do like a measurement of the entanglement, like a violation of the Bell inequality, you will always be on the fact that you have to assume fair sampling because the loss is there to hide. You cannot get the fully device independent. You can have the device independent with assumptions. So
by device independent, you mean you have to test some value?
yes, but I think, okay, I'm not expert on the device independent thing, but for what I knew, the fully device independent were also the loophole-free Bell inequalities. And you cannot have loophole-free Bell inequalities if you have too many losses. Because you have to assume that your adversary is like controlling losses and just making arrive only when she wants it. And so if you don't assume the fair sampling, it means that you are sampling fairly from your angle pair. You cannot have fully device. And I don't think there is much research on device independent QKD on with entanglement. What people are most interested in is measurement device independent. Yes, because the actual attacks you can do on QKD are on the measurement system.
So you have some trust on the preparation.
Yes, you have trust on the preparation part, but the measurement part can be completely untrusted.
The high altitude balloon,
Yeah.
take into account is sort of like.
We take into account the pointing error. It means that you are not pointing well from the balloon to the ground station. And yes, we take into account in the model, and the parameters we used, they were mostly taken from an experiment that the Chinese were doing with the balloons. So we try to take into account this problem that the balloon is not fixed. But you don't, for example, for the uplink, you don't have other problems. You have the pointing, this expected balloon is not well fixed, but somehow you have a beacon signal, so you can adjust this thing. And what you have is what you consider is the residual, what you are not able to correct with your beacon. Yes.
Are losses from building or uplinks safe?
Okay, that is a little okay. Roughly saying, there are different problems. The problem with the uplink is that you cannot. Okay, let's say in the downlink, you have your wavefront is bad. And you can think that the same happens to the uplink. But the uplink, you have just you are sampling one small portion of your wavefront. So what you have is that intensity also of your wavefront is not like flat or is not Gaussian, but is like I would say very randomly is random. I would say if you sample a very small part of the wavefront, you see it as scintillation. So you see that your transmittance is going out, up and down. Okay, you want to say, okay, you want to do adaptive optics on the uplink. You needed to do send a beacon from the satellite to the ground station. You can pre-compensate the effects of the atmosphere, so that when you arrive, in principle, you have a plane wave on the side front of the satellite. The problem is that okay, if the satellite is moving, actually okay, assume that you have a low satellite, so it's moving quite fast. The direction in which you are pointing your satellite, so of your uplink channel, is different from the direction from which you are receiving. And that difference gives you an error in the estimation of your wavefront from the ground station that translates in an error on how you are correcting the effect of the uplink. And this is reducing how much you can adjust the effects of the atmosphere. And this effect you have for the uplink and you don't have for the downlink, because for the downlink, actually, the beacon and your quantum signal, they're seeing the same atmosphere. So the main difference is that for the uplink, you are not sampling the atmosphere that your quantum signal is crossing, but you are sampling an atmosphere that is a little bit different because it's on a different angle. While for the downlink, your beacon and your quantum signal, they're actually taking the same channel, and so actually you are correcting well your quantum signal. That is the main difference between downlink and uplink. And it's very strong for the low Earth orbit satellite, and for the GEO is less strong because this pointing velocity aberration is lower, but still you can see it. Yes, actually, okay, the people we are working with in ONERA, they are quite expert in uplink, but they are studying it for classical communication. Because people in classical communication are very interested into it because optical links, they can increase a lot the bandwidth. And so they're doing a lot of research on how you can make a very high bandwidth optical communication channel between geostationary satellite and ground station. So they are doing quite a lot of research on the uplink because of that. And that research is actually the problem for the quantum is the same.
The final goal needs to be, for example, to communicate between Italy to Indonesia, right? And you pass it to the satellite and the satellite to Indonesia.
Yes.
That is the main goal, right?
Yes, that would be the main goal. For the moment, for satellites, they are going more towards like shorter distance because they want to, if you want to send an entangled pair, at least for the technology that we have now, we need to have both ground station on site from the satellite. So this is, for example, the Chinese, they were doing the entanglement basically quantum distribution between two stations in China. And when they were doing the intercontinental one, they were using the satellite as a trusted node. Means the satellite was exchanging a key with China, and then it was going on top of Vienna, it was changing another key on top of Vienna. But then when Vienna and China wanted to communicate, they had to see that the satellite was trusted. So if you want to do a dynamic distribution, you need a line of sight between the satellite and the two ground station. So this is still something that you need. Of course, the higher the satellite, the more distant you can go between the two, but also the more tricky is to receive something actually.
There is one more question from about the key rate simulation.
Yes.
Can you give suggestion for our students how to start formulating the model for key rate simulation and making it better? Because different references could give different models, but actually they refer to almost the same system.
Okay, actually for the key-rate, we are based on papers with the security proofs for quantum key distribution. Mostly it is, okay, Okay, there are different techniques for continuous variables and discrete variables. For discrete variables, mostly is based on, okay, it's, I have to say, you need to dig a little bit into the papers that are estimating the amount of information that they are leaking. I mean, it's not, I would say, okay, let's say the problem of calculating the secret key for the satellite case is built on some results that you get from the security proof that tells you how much secret key you can exchange given a certain channel, given I would say, a fixed attenuation channel. And what the only difference that you have on satellite is that instead of having a fixed attenuation, of having like a channel that is fixed, so you send you have a fixed transmittance of the channel. For discrete variables, you take the average. So you calculate the average of the number of photons that you receive given the number of photons that you transmit, and you calculate the average key rate. And then you plug that into the formulas that you have for from the security proof. The security proof, they ask for a certain, they calculate the information that they're leaking as a function of the gain is like the fraction of received photons, of received bit with respect to what you said, and then the QBER, so the fraction of error with respect to the fraction of what you received. For doing it on a satellite, instead of using those, instead of being a fixed number, they are average, and you do the average with respect to the channel probability distribution. And once you do the averages, you plug them into the key rate formula and you get the results. For continuous variables, it's a little bit trickier because, I mean, that probably would require a little more than one answer because you have to take into account that the noise depends on the probability distribution itself. So you cannot just take the average and plug it into the formula. You have like to make some average and then some average of the state that you're receiving and then use that to calculate the information you're leaking. That is a little more tricky. I mean, if it's interesting, I can give some references on that. I think is the best solution.
Okay.
Yeah.
There are more questions from students. In the last part of your simulation, you are using software from that.
Yes.
Is it a free software?
Okay, NetSquid actually is okay, it's free. I think you have to register to the website. They have to give you access to that software. It's not the easiest thing, but I think it's if you are doing research, you can get it quite easily. It's
Is it more directed to experimentalists or theorists?
I would say it was built from theory people, and it was built from theory people that were doing mostly quantum networks, for example, using LV centers or diamonds and studying quantum repeaters protocols. So it was implementing a free space channel. Okay, it was not so difficult, but then if you want to do very long simulation, it's not the most efficient software. But yet it's doable, it's usable for doing. And the free space, one of the free space models is like open source, the viable one. The other one the one that the article exited in December, I think it will be open source at a certain moment. And the idea is to put it open source. Then, yeah, I don't know if it is already open source. It's on the GitHub, but I mean, the problem of the research is always that it's built to be fast, to get the results fast, and then if you want to release it, it's going to be a mess to use it because.
Any other questions, comments?
if there is no more questions, then let us give applause again to Matteo.
Thank you.
Well, we have something for you. Excuse me. Langkah. And my remind
Nggak sih? Ini bentar.
Thank you very much. It's good that our very first colloquium this year is opened by you. Talking about a very important content. Thank you.